Hi everyone, my name is Nick Russo, and today we're going to talk about IPv6. But we're going to take a little bit different approach as a lot of other network people might take, because I want to talk about some of the not necessarily niche features of IPv6, but I want you to look at it in a different light. So I am a technical leader at Cisco. There's a link to my website there, and let's get started. So I want to start with just a very basic, somewhat boring overview of stuff that everyone or most people already know about IPv6. These are the standard talking points or selling points that we've been hearing for probably close to 20 years about why IPv6 is better, why you should migrate to it, and a lot of the doom and gloom around if you don't migrate to IPv6, there's going to be all this horrible future for you and your company. So a few of those kind of factors are IPv6 is bigger than IPv4. So when we think about why is this relevant, probably the most important piece of this, or at least the biggest selling point, is that IPv4 exhaustion is upon us now. There have been various ways of selling and trading IPv4, buying IPs by the dollar or whatever currency and redistributing them to different companies who are not ready to move to IPv6. But broadly speaking, IPv6 is nearly inexhaustible, and people are generally quite wasteful when it comes to allocating IPv6 because it was made to be so large in the first place. So this gets around one of the biggest limitations with IPv4, but a lot of people don't actually have this problem. When we're talking about small companies that maybe only need basic internet access, or they have some kind of IPsec-based WAN overlay and they're just trying to interconnect sites, they may not need a whole lot of public IPv4 address space. So this kind of fear point doesn't really strike fear into people as often as a lot of IPv6 pundits would like it to. And for the record, I am very pro IPv6. But I think that the way that our community has gone about selling it and gone about promoting it and gone about demonstrating it has been not very good. Because we tend to focus on the points that you see here on the slide. So there are some other basic technical details about IPv6 that it can't be fragmented in transit. So there are some complex mechanisms that IPv6 uses to ensure fragmentation only happens between the end hosts. Namely, there are messages in ICMPv6, like the router advertisement, that can carry the MTU to the end host. So the end host can communicate that to the application, and the application can fragment packets internally or whatever else needs to happen. So fragmentation in the middle of the network, which is generally a performance killer on various routers with IPv4, that's not so much of a concern with IPv6. And these, again, are just minor advantages, I think. We also have just some more semantical type differences where in IPv4, we had a variety of different protocols to handle some basic link layer communications. For example, to map IPv4 addresses and layer 2 Ethernet MAC addresses, we typically use Address Resolution Protocol, or ARP. Most engineers are familiar with how ARP works. We also have Internet Group Management Protocol, or IGMP, also known as IP Protocol number 2 in IPv4, to signal between hosts and routers for multicast group membership. And it plays a role in just telling routers when hosts want to receive multicast. Pretty basic protocol. There's also ICMP Router Discovery Protocol, not very commonly used in IPv4, but it's somewhat like being able to communicate with your routers to learn their gateway information and discover who the routers are on the LAN segment. What we do in IPv6 is there was a desire to consolidate all those things together into ICMPv6. And this is a very broad and expansive and powerful protocol that can do a lot of different things. In IPv4, when we think about ICMP, we generally think about it in the context of pings and replies, and maybe some unreachable messages like administratively prohibited, port unreachable, host unreachable, time exceeded, a few of the basic ones. But ICMPv6 can do a lot more. It can do all those things, plus everything that ARP, IGMP, and IRDP can do, just with different names. So it encompasses a much broader scope. So we've kind of consolidated the number of protocols needed into fewer, but there is a lot of hidden capability within ICMPv6. So I'm going to talk about some of those capabilities. So this presentation isn't meant to be like some overly complicated discussion about all the IPv6 technologies, but rather it is meant to be a discussion about how we can use these technologies to solve different business problems. And then finally, there are a few things that simply don't exist in IPv6. We don't have any concept of stateful NAT between IPv6 to IPv6, because that's generally seen as not useful. And likewise for Multicast Source Discovery Protocol, or MSDP, that doesn't exist in IPv6 either. There are other ways to do rendezvous point redundancy within IPv6. So some protocols were just overhauled entirely. So that's just kind of a quick review on a few of the functional differences between v4 and v6. But what I think is more interesting is to point out things that v4 can't do at all or can't easily do without a whole bunch of extra unnecessary work. And these are things that IPv6 can do relatively easy. So I would challenge you to apply some creative thinking here and see how these can make your life a little bit easier. So the first is there's not an easy way commonly in IPv4 to signal the time to live, sometimes called the hop limit in IPv6, from routers to clients. So we have these other mechanisms like path MTU discovery and various other techniques of determining the MTU along the path. But in IPv6, we can signal that to clients. So that's a big advantage. Another one, and this is one of my favorite things about IPv6 in general, is that we can statelessly generate unique addresses. And we'll talk much more about that as we go and some of the use cases for this beyond just basic network management and network operations. We can also statelessly communicate non-address information. I think everyone in the IPv4 world has worked with DHCP, Dynamic Host Configuration Protocol, at some point in their careers. Most large enterprises use it quite extensively on their wired networks, and it's pretty much a solid requirement for just about any modern wireless network. So DHCP is pretty much everywhere. But DHCP and IPv4 is pretty limited to just handing out an IPv4 address along with some extra information, options as we call them, like what is the default gateway, what are the DNS servers, what's the domain name, what are my NTP servers, maybe a TFTP server, a few other basic details. But in DHCP v6, we can hand out everything except an IP. So we can hand out what is the domain name, what are the DNS servers, etc. And we can do that statelessly because that information isn't unique to a client and therefore doesn't need to be retained by a server. There's a very huge advantage to doing that. We can also allocate entire prefixes. So in IPv4, there is technically a feature called On-Demand Access Pool, or ODAP. I've been doing networking for at least a decade at this point in some pretty complex environments, and I've not seen ODAP deployed in real life. Maybe some of you have. But in IPv6, we have a feature called prefix delegation, which we'll talk more about later. So in IPv6, we can delegate entire prefixes to like a router, for example. And then that router can distribute that prefixes amongst its interfaces, effectively providing unique subnets to all of its different LAN interfaces, for example, and being able to basically provision a remote site using a built-in process to IPv6 rather than having to do some convoluted zero-touch provisioning system that a lot of vendors have created. There's also another thing, we'll talk about this as we go, but you can embed information inside the addresses. So if you've ever worked in a large-scale IPv6 multicast environment, maybe you've seen embedded RP, where the rendezvous point can be carried in the IPv6 multicast group, so we don't need some out-of-band protocol like Bootstrap router to try to communicate that information. So there's a lot of kind of cool advantages to IPv6 that I think some people look at these as just kind of silly tips and stuff, but in this presentation, we're going to talk about two real-life, large-scale, very well documented and well tested architectures that I've personally developed. And in this presentation, we'll talk kind of at a high level about how these architectures work, but towards the end, I'll give you references if you want to read the 30 or 40 page write-ups I've done on each one. So the first one is an unlimited scale WAN. All right, so now I sound like a vendor. I'm trying to sell something, right? Unlimited scale. No, really it is. And the reason it's unlimited scale is because it's stateless. So here are the requirements, and I'm not going to get into the details and where I got these requirements from and which customer and which environment due to operational security reasons, but this is a real life design that I put together for a customer environment where we were trying to solve a problem where we had an overlay network and an underlay network. And you might think of common features like Cisco's DMVPN or Juniper's Group VPN, and there are a lot of other overlay type technologies that could solve this problem, but none of them give the scale that we needed for this design. So we needed any-to-any connectivity, not through a hub. We wanted minimal maintenance, so minimum operations, administration, and maintenance. We wanted to put the routers out in the network and have them generally operate without a whole lot of troubleshooting. We wanted it to be easy to connect clients. So like those laptops you see on the high-level diagram, we needed a way to connect them easily without a whole bunch of complex configuration on them. We needed a way to optionally provide encryption because there were some parts of the network that simply didn't need it, but others that did. And of course, the encryption is going to introduce some scaling limitations, but that's neither here nor there. And we also need a way to interwork from the IPv6 network to an existing IPv4 network. So we can bolt on this new WAN to the network and have all these clients run in a v6 only environment, but they still need to communicate with legacy IPv6 services. So the broad solution here is to use 6RD. So 6RD stands for 6 Rapid Deployment, and it's typically used in service provider environments to extend IPv6 to customer routers, typically in a residential setting. And it works very well for that case. If you're familiar with 6-to-4 automatic tunneling, it uses the 2002::/16 prefix, then you know most of what 6RD is about. 6RD just makes it a little bit more flexible on what address ranges you can use, but the concept is the same. The thing that makes this interesting is that you can apply GetVPN or any other kind of underlay IPsec technology to perform an encryption of that underlay network. Of that overlay network, and we'll talk through that. To do the connectivity for the clients, we combine stateless DHCPv6 and SLAC. And SLAC stands for Stateless Automatic Address Configuration. And what we do with that is the stateless DHCPv6 will hand out, here's the domain name, and here are the DNS servers, which don't change. So we can pre-position that on all the routers, all those edge routers. And then we can use SLAC to perform the allocation of the IPv6 addresses to make sure that there is uniqueness across the network as well. So to go into a little bit more technical detail here, and again, this is not meant to be a deep dive on 6RD because this is a pretty well-known technology. And even if it's new to you, there's plenty of resources out there to explain it. But broadly speaking, suppose we have connectivity between these three sites over an IPv4 underlay network. So you can see I've got some IPv4 addresses here, like the 198.51 is the prefix, and then the individual subnets for them have the last two octets, which may differ. So I used easy numbers here just to make it a little bit easier to look at. And the way 6RD works is that you specify what is my 6RD prefix first. So maybe an ISP hands this out, or you get it allocated by your job environment. And let's just say that we're using that common 2001:DB8::/32 IPv6 documentation prefix for this presentation. And the prefix length allows us to answer the question, how many bits of the IPv4 address are the same between sites? So for example, when we look at the 32-bit IPv4 addresses from each site, in our particular environment, we can say with confidence that the first 16 bits are the same on each, which means we only care about the last 16. Therefore, we don't need to encode the entire 32 bits into our IPv6 address. We can only include the last 16 bits, the last two octets instead. What this allows us to do is you look, for example, on the bottom left where it says site prefix for the site labeled BR for border relay, like the internet gateway. We can have hanging off of that site, the prefix is 2001:DB8:10A. Now, really in IPv6, that's 01A. Sorry, it's 010A, meaning 1 and 10 in hexadecimal. And what that allows us to do is it says we're only going to take those two octets, the last two, embed them in band in the IPv6 prefix. So now any traffic from the other sites destined to an IPv6 destination within that 10A::/48 prefix will be directed towards the BR. So it's really cool, and it works just like the stateless 6-to-4 automatic tunneling, just more flexible on your prefix sizes and the addresses you can use. And the same is true for the two remote sites. And as long as you do this carving ahead of time, then as long as you have unique IPv4 addresses on every site, then this is going to work just fine. And there's no overlay control plane. There's no BGP, there's no OSPF. It's just a static route that allows all these sites to interconnect with each other by saying any traffic for 2001:DB8::/32 can be sent into the 6RD tunnel, and that's it. 6RD will then unpack from that prefix what the target destination needs to be in IPv4. You can see I have that little fabricated packet capture at the bottom to show what that might look like for traffic transiting from site on the left to the site on the right. This is just kind of a high-level example. Now, if we want to talk security, it gets a little more complex. So Get VPN is an any-to-any technology. It's Cisco-based, but it's based on the group domain of interpretation, the GDOI, I believe. And the idea behind it, without getting too much into it, is that we will have these centralized key servers. The group members at the remote end will register to the key servers, will download the IPsec keying information, and will be able to communicate in an any-to-any fashion using a shared IPsec security association, or SA. Basically, all we need to do when we identify our proxy ACL, basically what is the IPsec traffic that is interesting to us to be encrypted, all we need to do is specify what are the source and destinations within that IPv6 underlay prefix that we talked about earlier. So I say IPv6, what I really meant was the IPv4 underlay prefix that we are using for the IPv6 overlay of 6RD. So if you found this interesting, I'll give you a link at the end of the presentation, which will detail this architecture in much more depth. But this allows us to have a WAN that can scale to enormous size in an enterprise environment with security, while also providing an ability for the clients to automatically get their address assignments. Now, I'll talk more about the client addressing in this use case, because I think this one is also very interesting. So kind of similar to the first example, this second architecture was from another customer request I had a few years back about, we have all these vehicles in our fleet, whether it's mail trucks or Amazon trucks or military vehicles or first responders or whatever it may be, some kind of vehicle, and we want to have a wireless connectivity point in them so they can reach back to our main headquarters while they're on the move. And we have thousands of these vehicles potentially, and we don't want to manage each router individually for the initial setup. So it needs to be very low touch when we do our initial setup. We basically want to load a config on the device, ideally not having to create unique configs for each device, and then install them in the vehicle and drive away. So the broad approach here is kind of similar to this previous example where we're going to tunnel v6 over v4, but in this particular environment, we needed to provide an additional layer of security. So the goal was we only needed hub and spoke access at this case. So you look at the bottom there, those two nodes, those two laptops never need to communicate laterally directly. And in fact, that's actually prohibited by this design. So they must be centrally terminated per the requirements here. We also need the ability to support multiple transports. So in this example, I show a node that has a wired connection into a switch near to the left of where it says IPv4. And I have a dotted line to a wireless access point. So this device has a wired and a wireless connection that should be supported. The site should be fully dynamic. And by that, I mean we load in a golden config on the router and walk away. And that same exact config gets loaded on every other router, and we can plug it in and it just works. We also needed a way that once the sites are online, the day zero work is done. What if we want to do day one and day two plus provisioning from the top down using standard automation tools like Ansible or Python scripts, or even basic stuff like SNMP? We need that too. So the broad solution here was to use BGP over DMVPN. Now again, it doesn't have to be Cisco DMVPN. It can be any hub-spoke IPsec type technology. But broadly speaking, DMVPN is what we used here. And IPv6 BGP allowed us to exchange BGP routing dynamically over that environment so that the spokes could communicate their prefixes back to the hub. Now, on the surface, that doesn't sound particularly interesting. There are a lot of companies who do something very similar. But what makes this interesting is that we used IPv6 for this. And in order to provide unique IPv6 addressing to each site, we used DHCPv6 prefix delegation. Remember that every router has the exact same configuration. So it's not like a template that we are just churning out different variables for each site. No, they're all exactly the same. The device, once it comes up online and it forms its DMVPN tunnel, it will send a DHCP request to get a prefix delegated to it. It will then assign that prefix to its local LAN interface, and then we'll use Slack and stateless DHCPv6 again to provide addressing to the client. The end goal of this design was for the client computer to form a remote access VPN using something like OpenConnect or AnyConnect or StrongSwan or whatever, VPN back in to another router at the other end of the network, or a VPN concentrator, to get IPv4 transport. So it's kind of a weird v6 over v4, but then v4 over v6 a second time. And if you look in the middle of the diagram, you'll see a red tunnel inside of a green tunnel. That's a double layer of encryption which was required for this design. And IPv6 actually played a big role in making this possible. So to broadly describe how does the prefix delegation work, Just like a lot of common DHCP exchanges you see in IPv4, there is a for-message exchange. We have a solicit message, and then an advertise comes back with a prefix that came from a pool that you specify, and then the device will request it and get an acknowledgement. That's basically how it works. The remote site will collect that prefix and then apply it to its LAN interfaces. And this response, even though I don't show it here for cleanliness, also includes details like the domain name and the DNS server. This is useful because even though the router doesn't really care about those details, it can do something really cool. It can actually take that information and advertise it towards the clients statelessly. So now that we've got this prefix, how do we handle the routing? So just for the sake of this diagram, suppose I have multiple sites that are now online. The way I like to do this is we run BGP in a kind of half dynamic way. So in Cisco land, we call this the BGP listen feature. I know that in Juniper and other vendors, they have comparable features that have different names. The idea is that the remote site will initiate the connection to the hub. The remote site will then advertise whatever prefix was delegated from DHCP towards the hub, and the hub will send down some kind of summary address, like a default, or maybe a summary covering all the VPN headends to which the clients will form their remote access VPNs towards. There's a couple ways to handle the routing, but this is broadly what the approach is. The advantage of this approach is that this tunnel formation, and you can have multiple tunnels to multiple hubs if you have multiple different transports, but this design still works the same way because the basics that you all likely already know about BGP, manipulation through AS path prepending, longest match routing, local preference, MED, etc., those all still apply. So if you have multiple overlays with multiple routing exchanges, it still will work the same way. You just have to choose which, do I prefer my wired connection over my wireless? I prefer my wireless over my cellular backup, or I prefer my cellular backup over my satellite communications, or whatever it is. And it's very easy to adjust those BGP policies from a centralized point at the hub so that we don't have to keep touching the spokes. Now, how do we give addressing to the endpoints? So the broad idea here is that the client will send a router solicitation. Now, in ARP, we don't have a message like this because ARP is just for basically neighbor solicitations and neighbor advertisements in the IPv6 world. But within this environment, or I should say within IPv6, the router solicitation is the device asking, hey, who are the routers on the segment? The router comes back and says, hey, I'm a router. Here's all the details, the hop count, the TTL, my router preference, and most importantly, here's the prefix. And that same prefix is the one that was delegated from the DMVPN tunnel, ultimately coming from the hub site of the DHCP prefix delegation. So we are advertising that to the client, basically saying, here's the prefix that you can use to statelessly generate an IPv6 address based on your MAC address. So this is a process known as SLAC, and there are various ways of doing it. The EUI64 approach is probably the most common. This takes the MAC address from the client. It inserts a fixed number of bits in the middle, the FFFE part of it, and then splits the MAC in half with 24 bits on each side. There are other ways to do this that are a little bit less identifiable, different security extensions. It doesn't really matter because there's going to be uniqueness. But the client will get a unique address completely dynamically from a delegated prefix. But then there's also extra information that DHCPv6 can collect from the router. So when the router pulls down that delegated prefix, it can also import other stateless details like the DNS servers and the domain name. And because that information can be stored on the router, when the clients, even if there's 100 of them, if they all need, hey, what's my DNS server? I need to go reach out to the VPN headend to form my VPN. When we ask DHCP for that, those messages don't have to be relayed to the hub. They can be answered directly from this device, which will improve customer experience because they don't have to wait for those DHCP requests to go over what could be a very slow WAN. So ultimately, this design allowed us to scale a large, highly secure hub-spoke network, providing addressing to clients so they could form their IPv4 VPNs back to a headend and use their applications normally. So we used IPv6 as a highly dynamic transport in a high security environment, and it worked quite well. I want to talk briefly about automation. This is a hot topic, and oftentimes when we talk about automation, we do so in kind of a context about features, and we don't usually talk about IPv6 uniquely. Now, we're not going to review the Python code on the right. This is just a snapshot of the code I've written, and yes, the code is available publicly. But there are a few things that you might be wondering how I solved, because if every single device has the same config, how are we going to be able to differentiate between devices? How, when they send an SNMP trap or a log message, they're just going to come from some giant IPv6 address, and we're not going to know what device it is. So a couple of just basic local scripting on the device using Cisco's EEM or Juniper Slacks or whatever other language you like for your device. I have two scripts. One of them will automatically change the host name to be equal to the serial number, which is guaranteed to be unique, and another that will automatically determine a loopback 0 address, which is a /128 that is advertised into BGP. This way, each device will have a fixed loopback. Even if the prefix delegation changes in the future, there will be a fixed loopback from a management network that is carved up across all devices. This way, once the device comes online, we can now reach that loopback and do top-down management without having to rely on prefix delegation. That way, prefix delegation just becomes an avenue for VPN clients to form connections, not for operational management, which is a huge advantage. There's a few ways that we can continue our automation from here. One approach, which I think is kind of cool, is that we can log into our hub router and log in and say, show me your BGP table for all your /128s in the management subset or subnet. Once we find them, we can parse out all those information lines and then build them into an Ansible inventory file. Or if we don't want to use Ansible, we can just use them in our Python program to perform some kind of automation on every host. If we're doing some kind of offline approach, for example, our inventory specialists have gone and collected all the MAC addresses from the box of all these 1,000 routers, and here's this giant spreadsheet. We can build from the MAC addresses, we can determine what the IPv6 address is going to be just by applying the EUI64 logic. So just to show an example of what these outputs might look like, I have two scripts. One of them is called Ansible Inventory from EUI64. And I don't show the inputs here because it's a little bit sloppy. It's just a row of MAC, or a column of MAC addresses, I should say. But when you supply those MACs, the MACs get retained as original MAC, but then for each individual node in there, we're going to have the Ansible hosts that are going to have the IPv6 addresses. And then on the right, this is where we actually log into the router to determine what are the loopback 0 addresses that we want to manage. And those could very well be different for different devices. But in this case, it's fully dynamic because we don't need to input any MAC addresses. So I realized that was a lot, and I wanted this to be fun and kind of exciting to show you some of the new features about IPv6. And not even so much new features, but new ways of thinking about how this technology can work. So if you're interested in learning about those three things, here are some links you may find useful. The first is a link to the Unlimited Scale WAN document. And again, these white papers are professionally written and reviewed. They're about 30 to 40 pages long, take you an hour or two to read it. And it goes into much, much deeper detail on how all the pieces fit, including the details about the overlay, the encapsulation, QoS concerns, MTU concerns, all kinds of things like that. The second white paper there is on the second architecture I talked about, the low-touch mobile sites, and all the considerations that go into it, as well as a more detailed review of the automation we just discussed. Last, if you want to get your hands on the code to see how it works or make modifications for your own environment, you can go to that GitHub link where I have a couple miscellaneous IPv6 related automation tools that you may find useful. So thanks everyone for your time today. Hope you enjoyed the presentation and hope you have some new appreciation for what IPv6 can do. It's my honor and privilege to share my knowledge with you today. And does anyone have any questions or comments about what we've discussed? I'm happy to answer them.
Thank you, Nick. That was an incredible presentation. Thank you so much for that. So we do have a few questions coming through. So let's begin. Here we are. What is your opinion on how we address some network characters dropping extension headers, which inherently break some of the functions of v6?
Yeah, so this is an interesting topic because I think a lot of companies in general, when they think about extension headers, I mean, the word extension by itself implies something additional to a protocol. But there was a Cisco document I read a few years back, and I don't have it immediately available, but it stuck in my mind what the document said. And it said that you shouldn't view extension headers as being some esoteric addition to the protocol, but rather an intrinsic part of it. And some of these extension headers are actually really important. So things like the IPsec AH and ESP extension headers, fragmentation related headers. Yes, it's true that routers don't fragment in the IPv6 path, but the end hosts still do. And that's why the MTU is signaled in the router advertisement. So extension headers broadly are important. However, carriers are concerned about the security impacts because some extension headers are almost the equivalent of IP options, where you have like a router alert or source-based routing, hop-by-hop option, destination options. I say options, really extension headers in this context. But they look and feel like IP options, and we've been trained as network people to dislike IP options because of their impact on router control planes. So my advice to carriers would be consider the negative operational impacts of your customers before you carte blanche stop supporting extension headers, and be a little more precise in which headers are allowed through your network to allow customer networks to continue operating. So again, I don't know of any specific companies that have restricted this, but just like most things, you want to be intelligent and functional about what you allow and what you disallow, balancing the security needs of a provider with the operating business needs of the various customers.
All right. So great. Next question. Since IPv6 hosts commonly have multiple IPv6 addresses, is it difficult for the device to choose the source address when initiating connection?
Yep. So there's an RFC that came out. It's 6724, and I had to look that up because I didn't remember the number. But the old draft was called Behave. I don't remember what it stands for, but there's an entire process from 1 to 10 or however many steps are in it that describe how an IPv6 host should select a source address when sending traffic to a destination. So for example, towards the top of the list, if you are, for example, pinging your own address, then the source address is going to be whatever the destination is. So choose your own address as number one. As you make your way down, I think probably the most relevant one, at least in my opinion, is that when hosts have multiple addresses, so suppose I have one host with a global unicast aggregate address that can be routed on the internet, and that same host has some unique local or ULA addressing, and it wants to communicate with another host that also has those two types of addresses. Well, if the application is using the ULA address to communicate, then the device will source its traffic from the ULA. And if it's talking to a GUA, it'll source from the GUA. So if a host is trying to talk to something on the LAN network or within the enterprise, you could technically use either one. But if you're speaking to something on the internet, you're always going to use the GUA. So there is an RFC, again, I got the number here, it's 6724. There's a list that kind of illustrates how those different addresses work. And there's even a command, I don't remember it, within Cisco at least, where you can turn on a debug for it, and it will tell you its thought process on how it chose which address that it did. So you can test this by just spinning up a router, putting some addresses, sending some pings, and you'll see the implementation of that RFC if you'd like to verify it on your own.
All right. So we have time for, looks like, one more question. So we'll just run through that. So do network devices that run DHCP v6 PD automatically add routes to the local table as they assign v6 prefixes out of DHCP clients? If so, how do they appear in the local RIB?
They appear as static routes. So by default, in the example that I've shown, when the hub is the DHCP relay for a delegated prefix, that the hub will say, okay, I delegated prefix X/64 to this client. I'm going to install a static route with a next hop to that DHCP client's link local address for the X/64 prefix. In my specific design, I disabled that. And again, it is a static route, so it's relatively preferred over most other route types in just about every platform. And I used BGP to govern the downstream routing because remember, I had multiple hubs and they both can relay the prefix delegation and they can issue those prefixes down. But if certain links fail, for example, if hub 1 delegates you prefix 1 and prefix 1 is being used as the source for your VPN across the network and hub 1 goes down, well, hub 2 should still know how to route to prefix 1 that was allocated by the other device. Otherwise, your failover scheme is broken. So you can disable that on most platforms. It is installed by default as a static route, which makes rollout really simple. But if you have a complex, high availability, multi-link, multi-hub design, you may want to include some dynamic routing protocol, as I did with BGP, to govern that routing instead.
Okay, sure, that totally makes sense. So thank you. That's all the time we have today. Thank you for your presentation and thank you for your time, Nick. This has been incredibly enlightening. Genuinely appreciate it. Thank you very much.